Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 46, Liquids and Solids, Part 1. We are in Chapter 10 of your textbook. Here are our objectives for today's video. Pause here. So this entire chapter is going to be about intermolecular forces. We've discussed them a little bit specifically with gas laws, but now we're going to get into the specifics of them. So these are just forces between different molecules, meaning two or more separate molecules. And then in order to separate molecules from one another, we have to break intermolecular forces, so you must add energy. This is the reason why the process of boiling is endothermic. You'll see something called a heat of vaporization, where, for example, if you're boiling water, the water will rise to 100 degrees Celsius and then just chill there for a little while before it actually starts to boil. And that is because you have to add energy to overcome those intermolecular forces. More on that later. Right now, we're just trying to identify the intermolecular forces. Pause here. You do not need to draw the picture. Okay, so the goal of this video is for you to be able to look at the structure or the formula of a molecule and to be able to determine what type of force or of forces that it has. So we're going to identify 4 types of forces. The force is a dipole-dipole interaction. So this will occur between 2 or more polar organic molecules. So for example, this picture that I have here, it's probably HCl. So chlorine is more electronegative than hydrogen, so it takes on a partial negative charge. And then there is another HCl molecule nearby. The partial negative of one interacts with the partial positive of another. And then there is the intermolecular force. Whenever this happens, which will happen between 2 or more polar covalent molecules, you will have a dipole-dipole interaction. You'll see me abbreviate that to just DD oftentimes. Pause here. Right, so for the first one, the answer is no, because that is ionic. The second one, the answer is also no. Even though the CF bond is polar, CF4 that has a tetrahedral geometry shape to it is completely symmetrical. Therefore, the molecule is nonpolar. CF2H2, that is polar covalent. So the answer for that is yes. It is also tetrahedral, but it is not symmetric because we've got the hydrogens on one side and the fluorines on the other side. And then the fourth one is no, because carbon and hydrogen are considered to be equal in electronegativity. So if you just have carbon and hydrogen, it's never going to have a dipole-dipole interaction. Pause here. You do not need to draw the pictures. So with dipole-dipole interactions, the greater the degree of how polar the molecule is, the stronger the dipole-dipole interactions, which typically means we've got a greater difference in electronegativity. Then there is a subset of dipole-dipole that is so strong that we call it hydrogen bonding. We give it a separate name. This specifically occurs when hydrogen is directly bonded to oxygen, nitrogen, or fluorine, the 3 most electronegative elements. But the idea is the same. We have a partial negative charge on our electronegative element, for example, the oxygen on the bottom left-hand picture, and the partial positive from a neighboring hydrogen, and we form a very strong dipole-dipole interaction that is so strong that we call it hydrogen bonding. It actually is sort of like a half bond, hence the term hydrogen bonding. I want to point out that hydrogen must be directly bonded. It can't just be in the same molecule. So you could have hydrogen and oxygen in the same molecule, but if they're not bonded to one another, you won't have hydrogen bonding. Pause here. You do not need to draw the picture. So now our third type of intermolecular force, and this is thus far the weakest of the 3 at comparable molar mass. More on what I mean by that later. Even if you have something that is totally nonpolar, for example, CH4, there's going to be random, or not exactly random, but there's going to be constant movement of electrons, and you will have a partial dipole form for a fraction of a second, and then it will go away. So we're going to have this constant motion, and those constant motion produce temporary dipoles, and those temporary dipoles form London dispersion forces. So because they're temporary, they are not as strong at comparable molar mass to dipole-dipole forces and to hydrogen bonding forces. Literally anything that has electrons has London dispersion forces. Ooh, sorry about that. Take my phone away. Pause here. You don't need to draw the picture. And then our fourth and our most powerful force as ionic bonding. Notice I put bonding in quotes, and that's because it's not really bonding. It's a intermolecular force. So ionic bonding, this will occur with anything that is ionic. The greater the difference in charge, the stronger the quote ionic bond, and also the smaller the distance between the particles. More on that later as well. Pause here. So let's work through this. I'm going to use abbreviations here because I'm lazy. So it has electrons, therefore it is London dispersion forces, and then I have hydrogen directly bonded to fluorine, so this is going to be hydrogen bonding. I could also put dipole-dipole if I want to, but it's kind of redundant to put it if I've already put hydrogen bonding. For HCl, it has electrons, so London dispersion forces. And then this has dipole-dipole because I've got a polar covalent substance. It's not hydrogen bonding, though, because chlorine is not fluorine, oxygen, or nitrogen. So I could list LDF here. That wouldn't be wrong, but typically for ionic bonding, there's no need to do that because ionic bonding is just so much more powerful than London dispersion. So this has electrons, so has LDFs. This is polar, so I have dipole-dipole, not hydrogen bonding for what I don't have oxygen, nitrogen, or fluorine in there, and then the hydrogens here are actually connected to the carbon anyway. And then this one is just London dispersion forces because the carbon-hydrogen bond is considered to be completely nonpolar. All right, that is all for today's video. Thank you so much for watching and have a great night.